Welcome back to the YouTube channel for Wayne State University's chapter of the Tau Beta Pi Engineering Honor Society. My name is Austin Heitzman, and I am back again with another tutorial video for linear algebra. Today we will be looking at Chapter 1, Section 2, which covers matrices and elementary row operations, and it has a lot to do with what we looked at in the last video of Section 1.1, Systems of Linear Equations. So if you have missed that, I highly suggest that you go and check it out. But without further ado, let us look at what matrices are. So, a matrix is basically an array of numbers, right? So we can say an m by n matrix has m number of rows and n number of columns. So what does that look like? Let's say I have a 2 by 2 matrix, right? So an array of numbers with 2 rows and 2 columns. So I can just, for example's sake, plug in whatever numbers I want. I'm just going to say I have 0 and 1 and 2 and 3. That is a 2 by 2 matrix. Has 2 rows and 2 columns. What about like a 3 by 2 matrix? An array of numbers with 3 rows and 2 columns. And I get this confused all the time, so I really need to stop and think. We're saying rows this way, so I have 1, 2, 3 rows with 2 columns of just random numbers, for example's sake. And this can get arbitrarily large, so an m by n matrix, right, is essentially going to be a1, 1 all the way to a1 n, and then you can go all the way down 1m, and you will notice this sort of notation. So that's going to be, let me just make a side note so everybody's on the same page here. If I say A1, 1, right? This is usually generalized as saying A, I, J, where you have the ith row and the jth column. Right, so in that light, I've made a minor mistake here. So let's look at this again. So we have the first row in the first column. It's going to be this first number right here. I have arbitrarily many columns in between here. We're still in the first row, so that's going to be a 1. But now we are in the nth column. All right, so and now going down here, we're still in the first column, right? But we have arbitrarily many rows in between it. So this is going to be the mth row in first column, and once again arbitrarily many columns in between that. So the very last number right here is going to be in the mth row and nth column. So that's just like a notation that you might see, and this is a way to really generalize it. But in general, we're going to be seeing, like in actual practical examples, things with usually actual numbers in it. So you might be asking right around now, like, how does this relate to linear systems like we were looking at last time? So I have here like an example set of a linear system of linear equations. And if we look at this, we can notice that the way that this is laid out has a lot of extraneous information, right? So what I mean by that is that all of these like variables and the plus and minus signs and the equal signs and all of that, like that is giving us structure. But what we really need when we're looking at these is going to be these numbers in front, right? Excuse me. So as you can see, I've kind of split this up into 2 different parts. What we can look at here, what's going to be probably the most relevant, is going to be this green part right here. So I'm going to sketch out like an example matrix, just the brackets. And what I'm going to do is I am going to put just these coefficients into this matrix and lay it out as an array of numbers, right? So if I'm looking at the first equation right here, I can use that as the first row. So we have -4, 2. That x3 value is nothing there, so I'm going to put a 0 there, then the -3. Similarly, with that second one, 2, -1, -4, and 2, 0, 3, 0, -1, and always make sure to carry around like any subtraction signs as just a negative coefficient. And we have 2, 0, 0, 1, right? So I hope that it's clear that all we did is just like took out the coefficients of the system on the left side and stuck it as a matrix. And if you remember from a few minutes ago, if we are looking at m by n, rows by columns, this is going to be a 4 by 4 matrix, just to get that that notation into your head. And then so for this reddish pink part right here, if I draw out a tiny little matrix with one column, which is going to make this a vector, just a little key term for later, we see that this, I can just carry this over as 11 for the first one, -3 for the second, since that's the solution for the second system, second part of it I should say, 0, and then 4. Now, all we've really done is just break this down, right? So we've eliminated all of that extraneous information that I mentioned before, the variables, the operation signs, what have you, and we have stripped this down raw into a form that we can directly work with. Now, in order to really like show the relationship between this and this, we're going to form what is called an augmented matrix. And that is basically going to be a combination of this and this to show very clearly that this top row results in this results in that, and so on and so forth. And then doing this, when we actually go and try to solve it, that means that we're working with both parts at the same time so that nothing gets left behind. So an augmented matrix, excuse me, put this one in green, and I'm going to carry down the coefficients, so that was -4, 2, 0, -3, and so on. And then I'm going to draw this little line down the middle that's going to separate the coefficients from the solution part. So now on this side, I'm just going to write down that little solution vector that we just drew. And in order to signify that, I'm going to put this side of the bracket in that pinkish red color. So now we have an augmented matrix, and this is going to very clearly show the relationship between like that system of equations we looked at the beginning and this matrix right here. So the real question now is like, what do we do with this? And this is where it's going to get really similar, and we're going to ring a lot of bells from that first video. So there are 3 legal moves for matrix row operations, and they are the exact same things as what we talked about last time. So the first thing that you can do with matrices is you can interchange rows. So that row 1 could be interchanged with row 2, for example. You can also multiply a scalar into one of the rows. And a scalar is just some number. So we're going to say row 1 goes to some number C, and that is legal. And hope you remember from the last time, but we can also add multiple of one row to another. And in notation form, you can just say something like this. Alright, so like I said, this is the exact same thing that we dealt with last time. The only difference you're going to notice is that instead of saying equations, we said rows. That's going to be the same thing, right? When we're looking at matrix notation, you know, this set of equations is going to be the exact same thing as this. But what have we done here? We have made our lives so much easier, because now instead of like rewriting all of this with all of the variables and the operations every single time we do one of these row or equation operations, all we need to do is just write this set of numbers. So our carpal tunnel will thank us. Okay, so before we get into some examples, I just want to outline a few different forms of matrices. The first, like, really general form is going to be called the triangular form. And this, I'm just going to like kind of draw out a little example. So say that we have some matrix, right? If it is in triangular form, all of the rows that have like non-zero numbers, so I'm just gonna like write 2 and something. This can be interpreted as any sort of number in the middle. Basically, the diagonal of this is going to have like basically non-zero numbers. Anything below that, all of these are going to be 0, right? So this is going to form kind of like a little triangle, which is why it's called the triangular form. This is going to make a lot more sense once we start talking about the next forms, but I just want to give you an idea of like what to expect, right? So one that you probably have heard more about than triangular form is going to be row echelon form. And row echelon form is going to be a type of a triangular form of matrix. But notice with triangular form, like all these numbers, the diagonal, like it could be 2, it could be 0, it could be 3, it could be 45, it could be like whatever you want. You know, it doesn't really have any restrictions other than anything below those are going to be 0. For row echelon, there are a few different rules. So I'm going to just kind of sketch out a matrix as we go over these rules so that it all kind of comes together. So to say this is like an arbitrarily large matrix, the first rule is going to be that any rows that are entirely made up of 0 are going to be at the bottom of the matrix. So you're never going to have something where you have like 0, 0, all zeros above something that's like all ones, for example, right? That's a no. Instead, we want to set this up so that the all 0 rows are at the bottom. Just for clarity's sake, I think I'm going to make this like a 4-column matrix so you can clearly see what's going on. So the next rule, after we have made sure that all of the 0 rows are at the bottom, this is going to sound a little complicated until we really look at it, but basically any row with non-zero numbers start with 1. So I can't have something like 2, 0, 0 something, right? This has to be a 1. And any row with the non-zero numbers, the value that is the 1 at the very beginning is going to be to the right of the first non-zero number in the row above it, right? So to set that up, I'll make this a 4x4. So say I have 1, 0, 0, 1 at the top, right? My next row, if it must have numbers that are non-zero in it, and of course the first non-zero number in the row has to be a 1, I have to make sure that that second row is going to be to the right, right? So it's going to kind of look like that. And I'll put it like that. So as such, we're not going to put that last row with a 1 right here, right? Because that's not to the right of this. It's not to the right of that. So if we make this a 4 by 4, then that last one would have to be either here, or it could also be here instead, and that would be fine if this row were entirely zeros, right? And then the last requirement is going to be that any value below a leading 1 must be a 0. So there's no other number I could fill these spaces with. I can't do something like that. These spaces must be filled with zeros. And you'll see that this does make a triangular matrix, right? We have a triangle right below the leading diagonals that is entirely 0, right? So this is a form of a triangular matrix. It's a little bit more specific. And even more specific than row echelon form is something called reduced row echelon form. So basically, the same rules apply as row echelon form, but we're going to add another rule. Basically, in addition to all values below a leading 1 being 0, it also needs to be above a leading 1, right? So I can't have something like actually, I could have something like that, excuse me. Basically, if let me do it like this. If my leading 1 in the second row is going to be here, then this number must be a 0. I cannot have that 1 there, right? So something like this would be fine. No, it wouldn't, because this right here must also be a 0. So usually, reduced row echelon form is going to be somewhat of a something like this, right? It's not always exactly that form. It is totally fine if you have like this last row being entirely zeros, for example. But generally, if it has a clean one solution type of vibe, this is going to be what we're looking at. So when we were talking earlier about like the legal moves, essentially, in the long run, we're going to be using those to get the matrix into row-reduced echelon form. And that's because the system is solvable when a matrix is even in row echelon form, but it's going to be even easier to solve when it is in reduced row echelon form. And that's going to be because if you think about this, when we were talking about like the augmenting matrix, right? I'm going to just sketch out like a 2 by 2 matrix with some, a 2 by 2 augmenting matrix, I should say, right? So if I have this matrix in reduced row echelon form, a reduced row echelon form 2 by 2 matrix is going to look like that, and say they have solutions, right? Well, now, if my variable is, say, x and y, and this first column corresponds to the x's, and the second column corresponds to the y's, I immediately know that y must equal 4 and x must equal 2, right? Because if x is 0 in the second column and y is 1, then if the system equals 4, then y must equal 4, and likewise for the x value. So it's going to make it really, really convenient for us to just like look at it and be able to see what the solutions are. The second little note I just wanted to mention is going to be that all 0 columns that you have are going to indicate that that variable will be a free parameter, right? So if you remember last time we talked about free parameters being a variable that we kind of assign and a name, and it can go wherever it wants, and all of the other variables are going to be dependent on what that value is, right? So if I have something like this, I'm sorry, I want to change this a little bit, because we want all of our free parameters to be like the last variable, right? Well, now I see that this column is entirely zeros. So if this is an XYZ system, I know that Z must be a free parameter. We'll call it T, right? And then everything else is going to depend on that. So those are just a couple little things to keep in mind as you're working with these. And the more that you do these systems, the more you're going to start like picking up on patterns like that and understanding it. But I feel like having it in mind sometimes might help. So we're going to do a really quick, just one-off example on trying to get something into row-reduced echelon form. And this is because that's usually what you're going to be doing for a chapter like this. It's just kind of trying to get you familiar with like the row operations and everything. And once you're comfortable getting something into row reduced echelon form, then like the rest of everything is just going to be a lot easier and a lot more fluent. So let's just try this, right? So if you'll remember from last time, we basically mentioned that we want to manipulate this, right? So that we can kind of see what we're working with and it's easier for us, right? So just to remember the rules here, right? We need, if there's any entirely zero rows, they need to be at the bottom. That's going to be something we worry about later, right? Because we don't know that. We don't know if that's the case yet. We do know that any of these first values along the diagonal are going to be 1. And we do know that anything below that needs to be 0. So if you remember from last time, we kind of did exactly that, right? I mean, we looked at a system of equations. We started by trying to move it so that the the equation with a leading 1 is going to be at the top, because then it's just easier for us to manipulate the rest. And then we made it so that everything else below that is 0. All of section 1.1 was essentially preparing us for something like this, right? So let's just start trying it out. I see that my first move is probably going to be easiest to move this last row up to the top, right? So that I'm actually working with a 1. So I am going to interchange rows 1 and rows 3. And further, again, like I said last time, there's a lot of different ways to do this. So if you're going about it and you realize you're kind of tweaking a couple of the steps, as long as you get to row reduced echelon, it's fine, type thing. So just for my peace of mind, what I am going to do is I am going to negate what is now row 1 so that we're working with a positive 1. And so I don't make any silly mistakes, I'm going to keep writing this matrix out every step or two. So we have taken the first and third rows and interchanged them. And in the same process, we're also making that row a positive, right? So the row 1 is now going to be positive 1, negative 2, right? So we're taking that and negating it, putting it at the top. Second row stays exactly the same. And the last row is what used to be row 1. And you can already see, like, you're saving yourself so much writing, because instead of doing like the whole squiggly bracket and you have all the variables and operations, all you need to do is just write an array of numbers. So from here, my third and fourth step are going to be trying to eliminating these, right, so that we have zeros below that leading 1, as is part of the requirement. So it looks like I can do the exact same operation on both. I'm going to multiply the first row by a negative 3 and add it to the second row so that that becomes the new second row. And same deal with the third row. By doing this, that first row in practice is going to remain the same, right? We have not actually changed it, we're just using it to manipulate the rest. So if I have, and just like last time, I will write this out so that you can see what I'm doing. In our heads, we see that this first row is going to be multiplied by -3, so that's going to be -3, -3, +6, right? So 3 plus -3, that's going to give us that 0 we were looking for. -3 plus -1 would be a -4, and a 6 plus 0, 6. Likewise, we have -3 plus 3 is 0, -3 plus 3 is 0, that cleared out both of them, that's pretty nice, and 6 plus 1 is 7, right? Okay, so as you can see, we have already hit the triangular form, right? We have that triangular shape at the bottom that is entirely zeros, and everything above it is either 0 or non-zero. It doesn't matter as long as everything below those non-zeros are 0. So from here, what's our other requirement for reduced row echelon form is making sure that this and this is a 1, right? So this is something that we didn't really need to deal with too much last time, but the trick to doing this is to basically introduce some rational numbers, which isn't always ideal, but sometimes needs to happen. So for the 5th step, I'm going to work, this time we can do both of them at once if we wish, because this last row is just going to be, there's nothing else that we need to manipulate here. But just for clarity's sake, we will do it one at a time. So we can, we don't want to divide anything, but we can multiply the second row by the scalar. What is the, like the inverse of -4 would be a -1/4, right? Because if I want to multiply -4 by something to get 1, it's going to be -1/4, right? So I'm going to multiply that whole second row by -1/4 to get the new second row. Similarly, we will just do it all at once. We have 1/7 on that third one to get the new R3, because 1/7 times 1, or times 7 is just going to equal 1. So the first row again is going to stay the same. The second row, multiplying -4 times -1/4 is a 1, like we wanted. And then +6 times -1/4 is going to give us a -3/2. And that last row is just going to be 0, 0. 7 times 7 is just 1. So now you'll see we have the row echelon form. It's not reduced row echelon form yet because we still have these numbers up top that are non-zero, but we do have row echelon form. Nevertheless, the problem asked us to carry it all the way. So where do we go from here? Up to now, we have been kind of working from the top down to clear out everything below, right? Now we need to do what's called a back substitution. We're going to start at the bottom and then work our way up to clear everything else out. And this should be a little bit easier because now we don't need to deal with like adding things to the other rows. Those are already 0. So without further ado, let us look at step 7. Step 7, we can 7 and 8 we can do in one fell swoop because we are still dealing with the same columns. Basically, we want to clear these things out, right, to make them 0. So what can I do for the second row? I can add a positive 3/2, right? Since this is already 1, I can just say 3/2 of row 3 plus row 2 is going to give me my new row 2, because 3/2 minus 3/2 is going to equal to 0, right? And then similarly, we have 2 times row 3 plus row 1 is going to give me my new row 1. So, writing all this out, instead of starting at the top, because I know that that's all going to be the same, it's not going to be the same anymore. So we're going to start at the bottom, because the bottom is what's going to be remaining consistent, since we already have that where we need it to be. So the second row, this is still going to be 0. 3 halves times 0 is still 0, so this is going to be 1, because I was saying it's going to be a little bit easier going back up. And then 3 halves minus 3 halves is 0, so we got this second row where we need it to be. And for the first row, 1, this is still going to be 1, and then 2 minus 2 is going to be 0. Now just one tiny little step left here, because now we're almost there. We just need to eliminate this last 1, right? So that everything below and above the leading ones are equal to 0. So my last step, hope it's pretty clear by now, but basically in order to get rid of this 1, using this one, we can just add a negative of the first row. I know that's a little bit weird way to saying it, but essentially we're just going to be subtracting it. So I can do row 1 minus row 2, which is the same thing as saying negative row 2 plus row 1, if that is an easier way to think about it. And you'll notice starting from the bottom, we have this last row where we need to be, the second row where we need to be. It's going to be 1, 1 minus 1 is 0, and now we have all our boxes checked. So all of the rows that are not entirely 0 start with 1. The row above it is going to be to the left, right? So 1 up here is to the left of the 1 below it, and so on and so on. It's going to be kind of cascading that way. And then the entries below and above are all 0s. So we're good, right? We've successfully put this matrix into reduced row echelon form. And you'll be able to see now that, like, were we to have like some sort of like numbers here that acted as solutions, we could very easily say z equals 2, y equals 5, x equals 6, for example. So that's kind of the beauty of all of this. And we have done a lot less writing than we would have if we had to have left this all in systems of linear equation style. So I hope that this has cleared some things up for you. If it's still a little bit shaky, I highly recommend you just like start hashing out as many problems as you can. It will all start to click into place the more practice you give it. So thank you so much for watching. If you need any more help with some STEM-based classes, be sure to check out the rest of the channel where we have all sorts of engineering study videos. And stay tuned next time for section 3 of this same chapter. Thank you. Bye.